Hello students, we have been discussing about the centripetal force, the centripetal motion, centrifugal forces and all that. So let's now try to understand about the kind of rotation. What all will be the types of rotation that we'll get, what all will be the free body diagram, that is the forces that will be acting on any object and so on. So taking that further, we'll try to understand about the angular rotation. So let's understand what exactly are going to be the types of angular rotation.
The next thing that we need to understand is we have already understood about the force, we have already understood about the torque. Now let's try to relate that to the work. Obviously, this is what we are going to actually measure. This is a physically determinable quantity. So when we talk about work, so the work done by torque, an object which undergoes an angular displacement, let's say from theta 1 to theta 2, that is going to be given by, means you integrate it from theta 1 to theta 2, and this is nothing but the torque. The torque acting along the z direction into d theta. So tau d theta gives you the amount of work. So when you displace any particular thing from an angle theta 1 to another angle theta 2, then that produces a net amount of work. So the net amount of work on integrating gives you tau into delta theta. So this is the work done by a constant amount of torque. So this results into a similarity. So this gives you a similarity between the normal work done that you have already understood, or in the case of linear force, into the displacement. So that is similar to this. If you have to talk about the work energy theorem in this case, it goes in an exactly similar way. You don't even have to derive it. You already know that it is half mv square, half mv final square minus half mv initial square. So just change the velocity into angular velocity. So once you change that velocity into angular velocity, you can write it in terms of the moment of inertia. The moment of inertia is not changing, neither the radius of gyration is changing. So using that, you can just write down the difference in energies as equals to half omega 2 square minus half omega 1 square. So this looks the same like the work energy theorem that you had in the case of translation. And the rate of change of work done with time, that gives you the amount of power. So the power that is produced is equals to the amount of torque into the angular velocity. The amount of torque into angular velocity gives you the amount of power that you have. So that tells us as to about what all are the energy, what all exactly is the energy that exists in a rotation motion and how much is the power. In the next part, we will be discussing the most important part of the rotation motion, which has the maximum amount of application, that is the angular momentum and its conservation.
So students, we learned about the types of rotation and therefore the type of kinetic energy and the linear kinetic energy and the rotational kinetic energy. The rotational kinetic energy depends on the moment of inertia. Ultimately, it is going to be dependent on the mass, but if you look at it, there is going to be a factor which is going to come from the moment of inertia. Because when we are talking about linear kinetic energy, it depends on the motion of the center of mass. But when we are talking about the moment of inertia related rotational kinetic energy, that is going to be related to the rotation of the object, and therefore the symmetricity and the orientation of the masses is going to be playing a role. So that combined together will give you the total energy of rotation. Hopefully that was clear. Now we'll take it further and try to understand that in the absence of force, what is the kind of motion that is going to be shown in our next module. So please be tuned in.